I was just going to start with a lot of basics for LabVIEW, like how to actually use the interface, and then we'll just sort of move right into some basic stuff with loops and how to store things in memory and how to work with time. Does anyone have any questions before we start? Okay, well, then we will start. So if you've got LabVIEW, go ahead and open it up. Okay, anyone still waiting for LabVIEW to turn on? Okay. Okay, now can you see my tablet? Can anyone see the word test that I just wrote on the board? Okay.
Yes.
Awesome. That is working. Okay. So let's go ahead and, oh, other people can draw. Oh, that's weird. How's that? Okay, you're just like drawing through Zoom. Perfect. Okay. So what we're going to do is we're going to open up just a blank VI in LabVIEW. And VI stands for virtual instrument. Basically, it's LabVIEW's nomenclature for a program. And the easiest way to do that is just go to new, or you can also go to file, new VI. Either way gets you to the same place. And what you'll see is there's whenever you open up a new VI, there are always two windows. Like no matter what, there's always two windows. You've got what's called the front panel, which is the gray one that is up here now with the sort of grid lines. And then you have the block diagram, which is sort of this blank white canvas. The block diagram is where you actually write your code. And then the front panel is basically, it's always your user interface. So it's how you can interact with the code or display values or control anything. One thing to note is that you can always close the block diagram. And if you want to open it up again, you can go to Window and do Show Block Diagram, or you can hit Control-E. However, if you close the front panel, it closes both of them. So closing the block diagram will only close the block diagram. Closing the front panel will close both windows. I'm just going to open up a new one. Okay. So what we'll do first is we're just going to add two numbers together just because it's an easy way to look at things. So if you right click anywhere on the block diagram, you're going to get what's called a pallet. And if you just right click, then if you click somewhere else, the pallet disappears. If you right click and then click the little push pin, the pallet will stay open. So I'm going to do that. And the other thing is if you go up into the upper corner and hit the question mark, you'll get a little help window. And as you mouse over pretty much anything in LabVIEW, you'll get a little bit of a description for what's going on with the help in the help window. Does everyone see that? Okay. So you guys can unmute yourself unless you get like a lot of feedback. That way I can sort of hear whether or not you're following along as well. So in order to do math, you're going to go to the numeric palette. And let's just add two numbers together. So we're going to grab an add block. And we're just going to place it on the front panel. And what you'll see is the add block has three, they're called terminals. You have two inputs and you have an output. And if you look you've also got the help that showed up when I moused over it. And what it's saying is that you've got the X terminal, the Y terminal, and then basically the result, the X plus the Y terminal. And so what we can do is go back up a level. Sorry, go down here. So we're just going to add two fixed numbers together. So here we're going to grab a constant value. That's the this orange variable. And we can type in any number we want. So we'll do 42. And then you're going to mouse over this terminal, and you're going to get this little diamond shape. It's actually a spool of wire. And if you click on the terminal, you now see that you've got a little wire connected to your mouse. And you can now connect that to another terminal. Another way that you could get this little constant block is if you right-click on one of these terminals, you can say create constant. And now you've also got that same block that I just dropped into the other one. Okay. And so these are both constant, so they're always going to be 42 and 65. If we want to view the result of this, what we're going to do is right-click on the output terminal and say create indicator. And if we go back to the front panel, you can see that this is what was created. Can everyone see that?
Yes.
Okay. And if you double click this on either side, it'll basically jump you. So if you've got a lot of these indicators, you can double click to get back and forth to the correct one. And then before Amelie has an aneurysm, you can also right click on this indicator and say view as icon and make it smaller and not as ugly. So it'll work the exact same way, but a little bit cleaner. Okay, so right now the indicator says 0. So that's just its default value. We haven't run the code yet, so it hasn't added 42 and 65. The way that we're going to run it is if you go up to the upper left-hand corner, we'll see the little run arrow. And if we click it, it'll run the code exactly once, and we'll get the output in the indicator block. Does everyone see that? Okay. So let's see. The other thing that we've got is next to the run arrow, we have sort of these arrows in a circle. And if we click that one, it's going to run continuously. So right now, like the grid lines have disappeared. So this code is running like over and over and over again. It's just adding the same numbers together. So nothing's changing. And then to stop this, you're going to hit the stop sign. Now, one thing I'll mention is when we get to actually programming a robot, you should never ever touch either the run continuously button or the abort execution button or the pause button, actually. The only way that you should interact with running the code when it's actually running on the robot is with the run arrow. But when you're running just to blank the eye, just to try things out, feel free, go ahead and use any of those buttons. Does that make sense? Any questions on how to run a piece of code? Okay. So one of the cool things that you can do with LabVIEW is you can watch how the code actually executes. And so if we go up here and click the little light bulb and we hit run, what you're going to see is the data traveling. Let me go to run continuously so you can see it. The data traveling along the line. So the little data points are the little blobs, and they're going from, I set it up so that they're going from left to right, and you can see it going to the add block and then coming out as the result here. Can everyone see the little moving blobs? Can anyone see the little moving blobs?
The
Yes.
what?
The little dots that are moving the blobs.
Yes.
Okay.
Yeah, I can see him.
So here is perhaps the weirdest thing about LabVIEW, but also I think one of the most powerful. So LabVIEW is what's called inherently threaded, which means that everything that can possibly run in parallel is going to run in parallel unless you tell it otherwise. So if I rename this indicator A, I just copy this entire thing. And we'll do 26, 14. Which summation do you think is going to run first? The 42 plus 65 or the 26 plus 14?
They run at the same time.
At the same time? What if you have, so it can try, and on the RoboRio, it will be able to execute both of these potentially simultaneously. But there is a limit, so if you have more things in the computer run simultaneously, it's got to pick. How do you know which one is it going to run first? So it's a bit of a trick question. The answer is you don't, and there's no way to find out. So if we click run here, it is going to run both these in parallel. You can see that it actually calculated B before it calculated A. Everyone see that? Like the B number gets calculated before the A number.
Yep.
And there's no real way to know beforehand, instead of you can write your code like this, which one's going to happen first. And so this is something that we're going to come back to a lot. You do have to be really careful about what order things are running in to make sure that they're doing exactly what you expect. So, for example, we can force this one to run after. So right now, B, for whatever reason, LabVIEW picked calculating B before A. So let's see if we can force B to be calculated after A. Any thoughts on how we can force B to be calculated after A?
Is there a priority function?
Yeah, there's a.
So what if we made it so that the calculation for B, go ahead, Alex.
Oh, there's like the thingy that you do at the beginning and the begin thing.
There is, yeah, so there's something called a flat sequence.
There's like a flat thingy. Yeah.
There is. Okay, so I was going to do that later, but we can bring that in now. So here, before we bring in the flat sequence, which is an excellent option, I do just want to also say that if the calculation for B depends on something from A, that is another way to force it. So you can also put in another add here, and instead of having it be 14, you could have it be A plus 14. And if you connect, oops, that. So now it's going to, now if we watch it, it's going to require that A runs first before B happens. Does everyone see that?
Yep.
Okay. But to Alex's point, there is a way to do this. So if we right click again, and here I'll use the same palette window. We go to the structures palette. We have this thing called the flat sequence. And if we drag it around this block of code, and then if we right click on it and say add frame after, it sort of looks like a film strip, and the idea is that this frame of code is always going to run before this frame of code. So if we hit run again, it's going to do everything in this frame first, and then it will move on to the next frame. One thing to point out is that anything that's happening inside of the frame is still happening in parallel. So if we also have the same summation here in A, these two things are still going to run in parallel, and you don't necessarily want to execute. So it's really going to run this frame in parallel, everything in that frame in parallel, and then move on to that frame. Does everyone see that?
What do you mean?
How do I get that? Fill that box. Which one is it?
Flat sequence. What is this? It's a flat sequence. So this
Any
function,
questions on this one?
drag it out, and then go around this one. Okay, stop. And right click on this edge.
If you want to remove the flat sequence, if you just click on it and click delete, it's going to delete everything inside of the flat sequence, which you may not want. If you right click on it and say remove sequence, you can remove it and preserve the code that's on the inside. Let's see. Okay. So the next thing is, in most text-based languages, you share information using variables. And you do that in LabVIEW too. However, as I'm about to sort of show you, using variables can be a little bit messy sometimes. So every time that you create an indicator on the front end, you now have a variable. It exists in LabVIEW. So if you get a variable, you go back to the structures palette, and then you go to local variable house. And if you click on that, you'll see A and B. So these are the two variables that are available in LabVIEW. And they directly correspond to what's on the front panel. One of the annoying things is that if you want a variable, it has to be on the front panel. So there's no way to make a variable without it being on the front panel. So if we click A, and okay, so that's the other thing. So right now, A is an indicator. So you can take a wire and put the value into it. If you want it to be, you can also change it. Oh, sorry, it's in read mode, basically, write mode. If you want to change it to read, so this would now be the result from A. You right click on it and say either change to write or change to read. Does that make sense? So the sort of weird part about local variables in LabVIEW comes down to this execution order that we're talking about. So if we create a constant here, and we can call it 500, we are writing to variable A here and here. Any thoughts on what kinds of problems that could cause?
Overwriting.
Overwriting it?
Yeah.
You also don't know when, you don't know who's going to overwrite whom. So if we click run, so it looks like, we go back here, it looks like this part executed first, and then the last thing that A saw was the 500. But there's no guarantee that that will happen the same way every time. So, you know, if I sit here and click run a whole bunch, there's no guarantee that it's always going to end up at 500. It could end up as 107 sometimes. Does that make sense?
Hey, Luke.
Mm-hmm.
Quick question. How do I force the icon labels to show?
Like on your palette.
On your palette.
Or like these, like
yeah.
I don't think I had it.
It wasn't in options, I don't think, but I could just be dumb.
Any of your items, anything you looks like different than mine? Oh, we use window title functions palette.
I think we already have that, but let me check. Yeah, we have that. And then I tried label all icons, and that didn't work.
I'm not sure. I've never had it not come up with that by default.
No, I think you just, no, that didn't work. Never mind.
I'll look at it out and see if I can get back to you on find a way to do that. So it's just not showing, it just shows you the pictures and doesn't show you any of the words here.
Wait, did I just get it? Is that what you wanted, Dad?
Yeah, I think we got it.
I think, okay, so I'll tell you what it was later. See, okay. Keep going.
Okay. All right. Any questions on how we don't know, which order things are going to happen in with summations and how stuff gets stored in the variables? Let's see. So what you'll see me do often is that I very rarely use local variables. I tend to connect things with the data lines instead, because it's a little bit safer in the sense that it's easier to control exactly when stuff executes. So even though it can kind of look messier, I very rarely use the local variables in most cases. Pretty much everything I connect with wires. I guess while we're talking about, sorry, is there a question? So while we're talking about wires, there's a couple of things that you can do with wires. So you can add labels to the wire. So if you click on the red and say right click and say visible item label, you can label the individual wires. That can be helpful, particularly as you get wires that are really long. If you do something incorrect, so if I just grab another number and I try to plug it into this wire, you get a broken wire. So that's the dotted line with the X on it. So this won't run right now. And in fact, if you were to go up here and click the run arrow, instead of it actually running, it's going to give you a list of errors. One of the nice things is you can double click on that and it will highlight the section that shows that there's a problem. So to get rid of that particular error, I can just delete that if I wanted. Now we don't have an error here. We still have a problem though. It still won't. It sees that this wire is not hooked up to anything. You can of course just click on it and hit delete. You can also, if you have like a lot of these broken wires and you want to get rid of all of them, if you hold down Control D, that will get rid of all of the wires. Any questions on the broken wire or the error messages that you get when you click the problem? Okay. Let's see. Next one. You can add labels to pretty much anything. So pretty much any block you can want to click on and go to visible items and add a label. So I highly recommend that you label things. At the very least, like say this was some constant, the wheel of the robot or something, I would always put, that's in inches, right? So for any constants, I always at least put what the units are so that if someone else comes by and looks at your code, or they know what kind of number to put in. If you want to just add a general comment, what you do is you double click anywhere and you can then just type. And yep, you can just put comments anywhere. There are ways to do arrows. So if you hover over here and you get a little box. You can click on that and then point to something. Like, oops, maybe thought. There we go. I don't know. I think the arrows are kind of ugly, so I don't usually use them, but you can use the arrows. Okay. Any questions on sort of the comments, how to label stuff? Let's see. So the next thing I want to talk about is the different kinds of variables that you can have in LabVIEW. So the orange, so pretty much everything is color coded in LabVIEW by what's called the data type. And so orange is a number that can accept a decimal point. So we can have 15.7. And that's called a floating point or a double precision number. In LabVIEW, it's always orange. If we went back to the numeric palette, we also have blue numbers, which are integers. So you can type in a number, but you can't type in a decimal point. If I type in that decimal point, it automatically changes it to orange. So I won't even let it stay as blue at all. If you try to add these two numbers together, what's going to happen is you're going to get a little red dot. You see a little red dot? There's a little red dot showing up on your screen.
Is there any chance you could make your screen bigger? Zoom in a little bit?
Yes. Okay. Apparently not easily now without logging out of everything. Let's see. No, there's a way in fact you can zoom in. I don't see a way right now to zoom at all. Except maybe if I can try that. Kind of blurry for me.
Yeah, it's a little better.
A little better.
He'll just go really close. Don't worry about
I'll
it
just
anymore.
squint.
Yeah, he'll be fine. Keep going.
Okay. All right. Can you guys see the red dot now?
Yes.
Okay. So what that's saying is that there's a mismatch between the data types. So we've got the floating point with the decimal point with the decimal and the integer value. We actually don't have an error. So LabVIEW will run this code, and what it's going to do, if we create an indicator, it's going to create an orange indicator. So it's going to automatically do what's called a typecast and convert the 5 into a 5.0 before it adds it to 15.7. So this should work just fine, and there shouldn't be any problems with that. Now, just because it works fine in this case, I would caution always relying on LabVIEW to make the correct decision. And so it's generally good practice to do the typecasting yourself. And what I mean by that is you know that you're going to have to do this conversion from 5 to 5.0 in order to add stuff. What you can do is go to the numeric palette and go to conversion. And then you have all of these conversions, which is applying internally here. But we can go here to double precision. Now if we connect the integer to that and click it, we don't get the red indicator. And so the result's going to be the same. We're still going to have 20.7. LabVIEW did this automatically for us the first time. But at least now we're aware of it and it's not happening sort of behind the scenes. Any questions on that? Okay. One of the other things that we can do, I should have mentioned this earlier. So in addition to being able to watch the value sort of move through, when the code is running, you can also hover over the wires and you get a little key icon. If you click on that, you'll open up a probe display. And so that allows you to view any of the values inside of a wire. So this, this one has a 1 and corresponds to the point where I selected that. If I select another one, I'll get a 2. You can see both of these 2 values. And when you're working with the robot, because you can't do, you can't do the little light bulb when you're running it on the robot. That would also be. So if you want to see value running on the robot, using the probe is the way to go. Any questions on the probe? One other thing is when we put in this convert to double precision, I deleted the wire and wired it in manually. You can also insert certain blocks. So if I right-click on the wire, I can go to insert and then numeric palette and then conversion and double, and it just automatically puts it in and rewires everything. Any questions on that? Okay. So what I'm going to do is I'm going to save this file and I'm going to upload a Git repository they all have access to that will have all of the code that we work on in these sessions. So you can go back and download it yourself. So I'm just going to call this one. Any questions on anything I shared so far before we go on to doing loops and stuff like that? Okay. Now I'm going to go ahead and close this and open up a new PI. I'm going to go ahead and save it. Oops. Okay. So, as we saw when we clicked the run arrow, it just executed our code once. When we click the run continuously arrow, the code runs over and over again. That kind of acts like a loop, but it's not the same. And I'll give a demonstration of how that's not the same once we get a loop in here. So if we want to really run the code over and over again and have it be making new decisions each time, we want to use a loop. So in order to get to a loop, we're going to go back to the structures palette. And today I'm only going to cover while loops. In the session on arrays and clusters, we'll do a for loop. But for the most part, we can do almost everything a while loop. So you select it, and then you can basically click and drag, and everything that is inside of this box is going to loop. And what you've got are a couple of things. You've got this little eye here, which will count how many times the loop has run. And then you've got a stop button. And if we try to click the wrong error right now, we've actually got an error. And that error is that this stop button has not been hooked up. So your loop always has to have some way to terminate, just to stop running. And this can be anything. So right now, this data line is green. And green is a Boolean data type. So that means that it can either, so instead of being a number, it can either be true or false. So if we want a true or a false constant, we go to the Boolean tab, and you can see we've got true and false. Those are the only two values that this kind of terminal can take. And so if we drop a true here, and we wire it in, the way this is set up right now, as soon as this stop sign sees a true, it's going to stop running. So if I click run, it's going to immediately stop. Like I hit run, and it just immediately stopped because you have a true run right in. If we click on this, we can change it to a false. And now, see how the run arrow is still, this code is currently running. You can either change it here. You can also right-click, or you can also click on this. Sorry, you get a little finger and switch it to be looking for a true now. So now with the false, if you click run, it stops immediately. And if you go to a true, it'll run continuously. Now, having a true or a false here is sometimes useful, and we'll cover exactly what situations that's useful for. But usually, you want it to be you want your loop to stop for some reason. And so, if instead of creating a constant, we right-clicked on it and said create control, we now have on the front panel a stop button. And so if we click run, right now we're running, and then when I click the stop button, the code stops. I'll run that one more time. Does everyone see that?
Yep.
If we want to see something happening inside of our loop, the easiest thing that we can do is we can right-click on the eye and say create an indicator. And now, if you click run, you can see that that number is getting very large very fast. So in the amount of time between me hitting run and hitting stop, the loop ran 71 million times. Everyone see that?
Yep.
Okay. So typically we don't want our loops to run super duper fast. There's a quirk in LabVIEW where if you have a loop like this, in order to run as fast as possible, it's going to take all of your available CPU power. It's going to go out and steal all of it, all of your other programs, and all of your other code in order to make this loop run as fast as it possibly can. And when you're running the robot, you don't necessarily want to be running the CPU at full power all the time, and it can also be affecting the other code that's running on it. So what we want to do is make sure the loop doesn't run super, super fast. And so if we right-click again, we can go to the timing palette, and we can go to this millisecond wait. And if we drop that inside the while loop, and we right-click on it, we type in 1,000 milliseconds, so that's equal to 1 second. Excuse me. What's going to happen is the code's going to run, It's going to wait 1,000 milliseconds, and then it will loop again. So now if we look at the counter, we should be incrementing every 1 second, roughly. Everyone see that? Any questions on loops so far?
I have a question about like the clocks. Like, what's the difference between all of them? Because there's a bunch.
There are a bunch of clocks. That is an excellent question. For the most part, I don't actually use that one for anything. Oh, that's actually kind of clever. So for the most part, we use this one, and this one is a wait. So this one does what we just saw, where it's going to pause the code until it's been at least that amount of time. Now, one thing I should also mention, right, is I do this and type in 2,000 milliseconds. How long do you think this loop's going to wait for?
2 seconds.
Yep, 2 seconds. So it's not going to add these two. So it's going to wait for a second, and then it's going to already have been waiting for the 2 seconds. So by the time it gets to the end of the 2 seconds, it's finished this one too. So this will be 2 seconds. So they run in parallel too. The other clock, I'm also going to explain here in a second. This one is an actual clock that tells time, and we'll talk about that one here soon. That's a good question. Really. There's a lot of them pretty much just use that one and the wait clock. Any other questions on this part so far? Okay. So I'm gonna, if it doesn't wait for as long, I'm just gonna make it wait for 20 milliseconds. That's enough for the computer not to freak out. It'll still run fast. Let's have it do something, have the loop do something interesting. So let's do math again. Math's always fun. I'm gonna do another add. We're gonna have our indicator. I'm gonna call this in loop indicator. And then I'm gonna have a little stint of 5. And then I'm gonna, instead of making constant, I'm gonna create a control. So this also shows up on the front page, except that instead of being an indicator, it's something that we can type into and actually change the value of. And we delete that so we don't have it. So now if we click run, right now we have the code is executing, and we've got a 5 on that indicator. I'll type in a 3, we get 8. Type in an 8, we get 13. Type in a 1, we get 6. Right. So we've now built a little bit of a button to add 5 to the number that we choose. Does that make sense to everyone?
Yep.
Okay. And I'll click stop. So now here's another question. So if I were to create, if I go here and drag the wire to the edge of the while loop, we get what's called a tunnel. And off of that tunnel, I can also create an indicator. Okay? And that indicator right now is set to 0. We haven't run the code yet. And we call this the out of loop. Any guesses on what that value is going to be when I hit run, as soon as I hit run on the out of loop indicator? Alex, I'm gonna put you on the spot. What's your guess?
No, I like looked away for like 2 seconds to drink my drink, and now I don't know what the code's supposed to do.
I'm so glad you called on her.
Wait, you should flash the screen.
So we've got 2 indicators. We've got one that's inside the loop, and we've got one that's outside the loop. right now we're inside the loop, we're going to be adding a 1 plus a 5. We know that the in loop indicator is going to be 6. What do you think the out of loop indicator is going to be?
6.
Let's find out.
Probably wrong.
Well, what does it say right now?
Well,
It's a 0.
is that because we're not
0, right?
updating it?
So this out of loop indicator is not getting updated right now. I mean, I can continue typing in numbers and the in loop indicator works. But if we were to turn it all light on, what we can see is the value. Here, let me stop this and oops, make this a little bit more obvious. So, why did that not? There we go. Okay. So we're getting the 8 here, but you can see how this line is still grayed out. The data are not getting to the outside of the loop. Everything is staying inside the loop. This value is not going to get output until the loop is finished. So what we can see is, so if I click stop, now the data is going to travel along the line. Now we get an output, and now our out of loop indicator matches our in loop indicator.
That's cool.
Yeah, so anything that's happening inside the loop can't be sent outside the loop until the loop is done and complete. Does that make sense?
Mhm.
Right. That will come up as a pretty consistent theme as we do other things. Is how do we share information between loops and get information out of loops? We'll talk about that later when we do more complicated stuff. Okay, so one of the things that loops are good for is doing things automatically. So one of the sort of classic things to do in a loop is to count. And let me think about how to do this here. So if I just create a constant, oops, 0, and I wire it to the input of the loop, I can basically start this loop with some value. Okay? Or I can start this is also a tunnel. So if we click run here, the first thing that happens is that value gets transferred into this tunnel, and so now you can probe that value. Currently, you can't probe that terminal. But so there's a 0 sitting here. So
You get control.
So one of the things that we could do is I want to add a number to this 0 every single loop time, every single time the loop comes through. So let's add, so 1s are easy, let's do a 1. And let's look that up. So right now, if we run this, we've got a 0 coming through, and we have the 0 coming through, and we've got the 1. And right now, the same thing is happening every single loop cycle, right? We bring in the 0, we add a 1 to it, we get the update in the indicator, and then when we hit stop, it'll eventually come out to 1 on the out of the indicator. That in and of itself is not super useful, right? Because it's doing the exact same thing every time. What we really want to do is start to have memory. So we want to be able to remember what we did last time and do something different the next time. So the easiest way to have memory inside of a loop is instead of having tunnels, which that's a tunnel, you can right click and say shift register. You see how we've got these two arrows on either side right now? Anyone see those? So we can also look up a constant.
You add a shift register
And now, if I were to take the same block of code
in there.
and add one to that one, I'm going to go ahead and make a new indicator here. So we'll call shift register value. So I'll go ahead and oh, I can't run on this one. Okay. So ignore this line right here for now. Just pretend that line doesn't exist. So right now, if I run this, sorry, what was it? Right now, if I run this code, it's the same thing. It's acting the exact same way, right? So we still have just always ones in both of these outputs. We're still just taking a 0 from the beginning and adding a 1 to it, and the answer is always 1. Now, instead, I'll get rid of that line. We take the output of the summation, and in addition to wiring it to the indicator, we also wire it to the other shift register. What's going to happen is this value is going to be 1. It's going to go in the shift register, and it's going to basically jump it back to the beginning, and now we're going to have a 1 here, and then we're going to be adding 1 plus 1. So if we run it now, we're now adding the previous value to 1 over and over and over again. And so we can look at that a little more detail here. So we start out with a 0, we add in the values, we display them. See, now it goes into that shift register and it jumps back, and now we've got a 1 here. Now we're adding 1 plus 1, now we have a 2. And in a second, well, we should get to a 3. Yeah, we just got to a 3. So these shift registers essentially allow you to remember values from the previous cycle. Does that make sense?
Yep.
Any questions on that usage of the shift registers? Okay. So to show you the difference between the run arrow and the continuously run arrow, we can use the shift register to sort of show us that difference. So, right, if I run it with the run arrow right now, we count up values, right? Now, in order to run it as with the continuous arrow, I do need to go here and change something. I need to make it so that the loop only runs 1 per code cycle. Well, actually, here, I've got a better idea. Leave that button there. Okay. So if I click run continuously, what's happening is we're still counting up. But now if I hit stop, see how all of a sudden it reset the counter?
Nifty trick.
So sort of a nifty trick, but also it can be kind of annoying. So so what's happening is when you hit the run continuously arrow, it's going to run this code. This code doesn't end until you hit the stop button. Once you hit the stop button, it's going to run the whole thing all over again, including these initializations. So if you start out with a 0 here, when it runs again, get fed, the 0 gets fed back in and restarts the value. Sometimes that can be useful. You'll find that when we're doing stuff for the robot, this starts to become a problem. And so sometimes you have to get kind of careful with how you initialize the shift registers, depending on exactly how you're using them, because they can reset when you don't really want them to reset. Any questions on sort of the difference between the run arrow and the run continuously arrow? Okay. Let's see. What else do I want to? Okay. Yep. Okay. So I'm going to go ahead and let's look at the timers again. These timers are lots of fun. And then I'll go on to some other ways that we can save things in memory. So if we go back to the timing palette that Amelia was asking about before, we've got this tick count. This is a clock that starts running, that starts at 0 as soon as the code runs. I think that's true. I can't remember if it's between the time that the computer is booted up that day and the code running. There's sometimes some nuances there. But basically, this returns a value from some start time in milliseconds. So if we wire that into the loop and we create an indicator, and we hit run, yeah, okay, it must be from the time that the computer boots up or something. Because you can see how that, that was a bad example. So what's happening here is this value is only getting updated every time I click run, because the thing that's outside the loop is only getting changed right at the very beginning. It's not changing inside the loop. So let me do this instead. There we go. Now you can see the clock counting up in milliseconds. Can everyone see that? Okay. Now, this value is not, in and of itself, this value is not super useful, right? You don't want to be like writing in your robot code, okay, based off of this time, this long piece of time, do this other, make this decision, right? So what we want to do is make this time start when the loop starts. Does anyone have any thoughts on how we might make a timer that only that starts from 0 when the loop starts? So what we can do is, what if
Can't
we
you plug it into the I thing?
into the I thing here?
Yeah.
So the I thing is giving us the total number of times that we've run. So the loop is run 3,100 times. This is giving us the amount of time that it's been in milliseconds. So there's sort of two different units.
Wow, that's a big button.
So what if we remembered the time that we started the loop and compared it to the current time? So the way we can do that is we can take two timers, one that we're only going to run at the very beginning, so what I did by accident first, and in this timer, which is running every time the loop loops. And if we do a subtraction between these two, so this timer is the current time at all times, and this is the time that we started the loop. And if we display that value, now it starts at 0. Does everyone see that? This is saying that the loop has been running for 6,000 milliseconds or 6 seconds. Does anyone have any questions about we got that kind of relative time. Okay. So we end up using this kind of technique a lot, where we compare the current time to some saved time in order to get the time since something happened. In this case, it's since we started running the loop. But maybe we want to do something a little bit more complicated, like what if we wanted to start the timer after we've pressed a button, or after we've pressed a button, perhaps. So what we can do, let me see. I think it'll do it. Do this. Okay. Okay, so we're gonna do something that I'll show you another way to do it that we normally do it, but it's something called a latch. And so what a latch is going to do is it's going to save some value for us in memory based on some triggering event. And we're going to use the shift registers to store the memory. And our triggering event is going to be a button that we press. And the value that we're going to save is a timer value. And the goal is going to be when I press a button, I want it to start counting the time since that button press. Does that make sense? So let's do the following. So we're going to need a shift register. So we're going to right click on the while loop and create our shift register. And let's see. We're going to hook up this timer to the shift register. Yeah, we can do that. So it's going to start out with the value of the time at the start of the loop, just like we've been doing. So this is identical to this so far because we haven't hooked up anything to that end. What we're going to want to do is, so I'm going to have to skip ahead a little bit real quick. So we need a way to do something different based off of a button press. We have to make a decision based off of a button press. And I'm going to talk more about how to work with Boolean stuff next. Like that's like the next thing. So maybe actually we should just skip to, maybe we should do that first and come back to how to make this piece of code. Otherwise, I'm going to have to skip ahead. Does anyone have any problems just for moving ahead to how to handle true and falses and making decisions? And we'll come back to how we do timers.
Sounds like a plan.
Okay, cool. So I will save this and open up a new piece of code and we'll come back to it later. Okay, so the Boolean values are these true or falses, and in LabVIEW they're always green as their data type. And there are other ways to make decisions, but the easiest decision that you can make is if something's true, do this, or if something's false, do this. And so what I'll start with here is if we go to the comparison palette, we have this select block. And if you've ever looked at the robot code, you'll find that probably the most common block that we use is probably this select block. It ends up in pretty much everything. And you've got 4 terminals on the select block. You've got the question, so the true or false that's going into the input. And then you've got the value that it should output if it's true, and the value that it should output if it's false. So for right now, if we right click on this, and say create constant, false constant, and we're just going to create constants everywhere else here too. We'll put a 42 or 65 here and 42 here, and we're going to make an indicator. When I hit run, what value is going to show up in the indicator?
65.
Correct. So let's run that. So we get a 65. And if instead we had a true value here, when I click run, we get a 42. Are there any questions with how, and if we could, we can also sort of look at it with the probe, just to sort of see how it's making a decision. If I click run, it only passes through the 42. Everyone sort of see that? Are there any questions on this select block? We could make it a little bit more interesting, and we could right click on the constant, the Boolean constant, and say change to control. And so now we've got a button on the front panel. And so now if I were to run this, if I press the button, I get a 42. If I don't press the button, I get a 65. Everyone see that?
Mm-hmm.
Okay. So
pressing is true or false?
pressing by default, pressing is true. So when it's lit up, it's true. Getting the 42, and not pressed is false, and I'm getting 65. You can make it so that it lights up the other way and stuff. You can by default, it's pressing is true. So say that we wanted to follow what Mr. Shanafeld said, and instead make it so that the pressing the button is false. The simplest Boolean operation that you can do, so just like there's addition and subtraction, multiplication with numbers, there's a lot of different Boolean operations that you can do. And the simplest one is called a not. And so that's this symbol here. And so if we take this and replace it, and run this again, oops, it's going to do the reverse. So when you click the button, you're going to get a true here, and then it's going to not it. You're going to do false. Now we're going to have an output of 65 instead of 42. So let me do that in a little bit a more formalized way. Let's see if we can see this. Oh, that's broken again. Oh no, it's there. Okay. So can everyone see my notebook?
Yep.
Okay. So the different Boolean operations are as follows. So if I've got a not, you can make a table. So our input is A, and our output is C. Okay. Wait for that to sort of update a little bit slowly. We're not. Let me see if I can reboot this real quick. Okay, can everyone see that table right now?
Mm-hmm.
Mm-hmm.
So if our input is true and we run it through the not, we're going to get a false. And if our input is a false, we're going to get a true. So we'll always just get the opposite of what our input is. Any questions on how the not operation works? The next operation that we can have is called an OR. This one takes two inputs. We'll call our two inputs A and B, and then our output is 16. And there's four possible combinations for our inputs, right? We could have A could be true and B could be false. A could be false and B could be true. Both A and B could be false, or both A and B could be true. If you read or like as an English word, and you said A or B, what do you think the output would be for A is true and B is false?
True.
True, correct. What about A or B if A is false and B is true?
True.
And A or B if both are false?
False.
And A or B if both are true?
True.
Does anyone have any questions about how the OR operation works? And then the next one, the next major one that we do is called an AND. And it also takes into account two inputs. And I can't erase them. We have the same possible inputs. Someone other than Alex, what do you think the output is for if A is true and B is false?
False.
False. Okay. A is false and B is true.
False.
Are you saying you don't like my voice, Luke?
I love your voice, Alex, but I know you know the answer. A and B are false.
True.
True. So why do you think true?
Because it's false and false.
Interesting. So the way that and is defined is they would both have to be true in order to be true.
Oh.
So if we have both A and B are false, we're going to have a false. And then the only way we ever get a true is if both A and B are true.
Math classes lied to me.
So there are ways to construct logical operations where it would work if either A and B are both false or A and B are both true. So why don't we go ahead and make that thing, make the thing that Lindsay was thinking about. So we have all these logical operations in LabVIEW, and they're under the Boolean tab. So here we've got the and, the or, and the not. There are other operations too. You can construct any of these other Boolean operations using just an or, and a not. It's just sometimes convenient to use the other ones. So let's do everything with just ands and ors and nots. So let's do the following. So we're going to make some more of these. We'll have one input A, another one B, and we're going to try and create exactly what Lindsay suggested. Change that to a so right now we've got, we'll make this a lot. right now we've got two inputs, A and B. On the front panel, you can also right-click and get to a different set of pallets. Oops. And then we can also have a Boolean tab in the front panel palette. And here we've got things like buttons, and then we also have LEDs with little lights. And we'll use the light as the indicator. So this will be the output.
Make it really big.
Right. That large enough out?
Yep.
I'll make those a little bigger so you guys can see them too. Everyone can see those. Okay. All right. So let's start out with just an OR. So the OR is a little V symbol. And so right now, C is false. If I click A, I get it to be true. Click B, it's still true. Unclick A, it's still true. Unclick B, it's false. That makes sense?
Yep.
Right. And then I'm just going to replace this with an and so we can just see that again. So you can right click on something and go to replace, Boolean palette, and I didn't have to redo any of the wires. It just automatically inserted the new block there. Now if we run it, click A, doesn't light up until I also click B, unclick A. Any questions on the and? So, does anyone have any thoughts on how we might create what Lindsay talked about? We would only get a true if either A and B are both true, or if A and B are both false.
Am I allowed to answer?
Mm-hmm.
You could do the select block and then the two ands, but then one of them at the end of it would be not.
Okay, so let's try that. Let me see if I can understand what you're suggesting. All right, so we've got the select block when we're plugging in. When I'm plugging in. You have to walk me through it.
Well, I mean, I don't know if it'll work.
Let's just try it.
So if you keep the A and the B with the and you plug one side into, wait, that doesn't work. Never mind. Don't worry about it.
Okay. Does anyone else have any thoughts?
Can you repeat the question?
So the goal is to create, here. The goal is to create a magical operator that does the following. True, false, false, true, false, true, true. We get a false if it's true. If it's true, a true and a false. Also, if a false and a true, but a true here and a true here. So our goal is to try and create this operator using nots, ors, and ands. Does that clarify that?
Is there an equality operator?
There's an or, and if you do or.
There is an equality operator. We could do that. So Mr. Shanafield's suggestion is that we go up and we cheat and go straight to the answer, which you can use an equal sign. And we can plug in our A and our, and our B to that. And if we run this one, A and B are both true, we get true. We unclick A, we get a false. If we also unclick B, we get a true. So this does do exactly what we wanted to accomplish. I'd like to go back and still do this also with and, ors, and nots though.
Okay.
Does I have a question. Does it have to do with, do you negate an A or a B and then use it?
Yeah, you can. You can definitely. We're definitely needing a not in there in order to do this. So here we can do the first part pretty easily, right? So we've already know how to do it so that we get a true if both are true, right? That's our and. That is sort of basically we already know how to do this part, right? Oh, maybe that's not updating anymore. I have circled the, oh, there it is. Can you guys see the circle?
Yeah.
So we know how to do that part, right?
Mm-hmm.
So that's this.
I figured it out, Luke.
Okay, what's up, Alex?
Yeah. So if you take if you do two of the constants and then you hook them up into two separate ands, one of the ands you put a not sign after, and then taking the thing from the not and then the first and you put it into your or and then into your indicator thing.
Okay, so why don't you walk me through that?
Okay, so get another and sign out and then you put it underneath, yeah.
Okay.
And then you wire your A and your B into it.
Okay.
And then after that bottom and sign, you'd put a not.
Okay.
And then you put an or and you'd hook up it into the not and thing and then the and.
Okay. So like this?
Yeah, and then into your indicator.
Let's see. Okay. So if I click this, it will turn off, right?
I think. Did it not?
Doesn't look like it.
Wait a minute.
Right now, it looks like that one is true no matter what you hook up to it. Now I'll go back so you can see that.
Is that, yeah. Oh. Yeah, that wouldn't work for that case. Never mind.
Well, you're very close. So we need to move the not to somewhere else. Where do you think, where else can we move the not, perhaps? What if we put the not right before the ands? Right before the and?
What? Oh. Yeah, on both of them.
Do you see that?
Yeah.
So if we went in here, in both of them, exactly. So we went in here, and the not here. Now if we run it, okay, we're true when both are true. We're false when A is false. False when B is false. And we're true again when both are false. Does that make sense?
Yep.
So if we look at, the table here, what we've done is made, these two falses trues, and then applied an and again, right? So we just turned this case into this case, and then put in an or, so we can have both of them at the same time. Any questions with this? Okay. So I won't go into too much more detail on ways to construct stuff. But I will sort of just mention that your entire computer does only these operations. And everything that your computer does is based on a combination of all these operations. So you can create all of the math blocks, you can create all of the memory, everything, just using ands, ors, and nots. Any questions before we, I think, probably loop back to looking at lines. Okay, I'm going to loop back to the time. Okay, open that up. So if you want to open up the saved VI, you go to File and then Open, and it's going to remember the last location that you saved stuff. So we were working on loops of memory before. Okay. So I think the thing that we were talking about before we went down the Boolean logic rabbit hole was how do we start and stop a timer with a button, basically. So what we're going to need is we're going to need our select block, because we're going to need to change our behavior based off of whether or not the button is pressed. And that's in the comparison palette. We'll go to select. And we're going to go ahead and create our button. And let's see here. So we're going to have this same block of code that we've been using, where we're going to subtract some time from the current time. But what we are going to change is the time that we're subtracting based off of the button that we're using. So I'm going to delete that line, that one. And let's see. We're going to first duplicate what we had before with the button press. So, okay, so if we take this value and we hook it up in the false case, and then we also hook up the output to the shift register and put this into the subtraction, this should be exactly the same as what we've been doing. So we're going to have this clock time at the beginning of at the time the loop started. It's going to come in the loop. It's going to get selected because we're going to not have pressed the button. And it's going to be subtracted from the current time. And then the value that we're putting back into memory is still just this initial value. I'm just going to put a random value up top so we can actually run it. So we can run arrow. And so if we select run here, we've got exactly the same code that we did before. Does everyone see that? Mm-hmm. Now, if we select, now if we do press the button, instead of getting the old value, we're going to put a 0 in. And so now this is that value that was at the very beginning, right? This is a number from some arbitrary start point. And then, well, actually, I think if I uncheck the true button, it actually is not going to fix itself. Yeah, we can talk about that in a little bit. So we're actually now stuck looking at just the time from the time my computer turned on or whatever. So let's talk about how we would set the time now. So if instead of a 0, we put in actually, we'll just put in this exact same time, right? So this is the current time into the true case. We haven't changed the false decision at all, but now we are going to do something different when we've got the true in there. Let's see. So now if I hit run, this is the timer that we had before. But now if I hit 2, we're stuck at 0, right? Because we're subtracting this value, which is that one from itself. This line here is identical to this line here. So we're always subtracting the same number by itself. We're always getting 0. Does that make sense? Mm-hmm. Okay. So now if we instead click false, we're back to the timer that we had before. Or sorry, not the timer we had before. This is actually, so, oh, I guess I finished. That makes sense. Yeah. Now we have it so that when we hit true, we go to 0. But as soon as we hit false on that button, we start counting again, right? From the time that we released the button. And so if we were to go here and make this button behave a little bit different, I'll talk more about this later. So all I'm doing is changing it so that well, here, I just won't mess with that for now. So right now we built this timer that resets every time that you unclick the button. So you might imagine that you do the timer like that on the robot for, say, like this year, when the shooter wheel's spinning up, for example, we want to know how long it's been since it's gotten up to speed, so we know whether or not we can shoot. So it's going to start at some, close to 0 RPM, and it's going to get faster and faster. And we don't want to shoot as soon as it gets up to speed because maybe it's not quite ready. So maybe we want to wait for a second after it's gone up to speed before we start shooting. And so, this button would then be a trigger saying, hey, we've gotten up to speed with the shooter, start counting the time. And then once it's been a second, go ahead and do the next thing, which is shoot the ball. Does that make sense? Any questions about these timers? Okay. So what I want to show next is I want to do this exact same piece of code basically, but without a loop. So I'm going to go ahead and close. Basically, I want to show you there's 2 different ways to store values in over a period of time in LabVIEW. Yeah, 2 different ways to store memory, because the loop works for some things. For other things, it's kind of bulky, right? You have to have lots of loops everywhere. And so one way, other than the shift registers, to save values. So I will make another new VI. And I'm going to call it feedback. Okay. So the other way to save values in LabVIEW is with something called a feedback node. So,
I love feedback nodes.
Yeah, we use feedback nodes a lot. If we go into structures, you see this feedback node, and everything else in LabVIEW runs basically from left to right, except for feedback nodes, which run from right to left. So they go with the arrow, and that's why they've got a big arrow, because everyone's used to seeing things go this way, and the feedback nodes are actually going to go the other way. So what we can do, for example, is take our clock, and just like with the feedback node, you need to give it some initial value. And so we're going to start our feedback node with the timer value with this timer value. And let's do this. We're just going to not change anything. We're going to go ahead and basically connect the feedback node to it. So it's going to output the value that it has stored in memory, and it's going to loop around and store that value in memory again. So this value is not going to change. And then we want to be able to view that value right there. So we'll call this value in memory. Okay. And I am going to put a loop around it, not to remember things, but just so that you can see what's happening. So this is going to be super not exciting. It's going to have one value, and it's just going to stay there, right? We just initially put in that value in. Hang on one second, my battery is starting to die here. One second, I have to plug in my laptop battery. Battery's plugged in again. That was pretty funny. So, yeah, so right now we're not doing anything interesting at all. We're just storing that one value from the very beginning, and it just stays in memory. We don't do anything to it. So let's go ahead and try and reconstruct the timer that we made before. So you can take this timer and you can subtract from it value that's stored in memory. So now this isn't the value of it, that's the value in memory. Let's make another one. We'll call this the timer. So we've remade that initial timer that we first had, where from the time that we started the loop, we have the number of seconds since we started that loop. Any questions on that part? Okay. So let's finish making that duplicate timer. So we're going to need our select block again. We're going to need our button. And then if the button's true, we're going to take the current time. If the button is false, we're going to take the time that we have stored in memory. And instead of just looping the memory around, maybe the output of the select block. So that way we can change the value that is stored in memory. And then, yeah, the subtraction should be the same. So now again, you should be able to hit the button, put a 0, and then click the button and restart the timer. And you can look at this one a little bit easier with this. So we've got the false coming in. False coming in, it takes in the value that's stored in memory. And that's the one that it uses for the subtraction. Whereas if we take and press the true, we've got a true here. It's going to take the current time and pick that instead. And that's what's going to get subtracted from itself. And so we've got the 0. So that and this we call a latch. In other words, we have some sort of trigger, which is this button, and pressing it takes some value and stores it in the memory. And that value is not changed until the next time that we hit some sort of trigger. And one of the most common things that we use that for is for keeping track of time. Are there any questions with